Hello. Hola. Hola. Bon dia. Bon dia, buenos días. Benvinguts i benvingudes tots a l'Escola de Camins, l'Escola d'Enginyeria de Camins, Canals i Ports, en una de les conferències d'aquest cicle de seminaris que estem organitzant pel 50 aniversari. Si em permeteu, faré la presentació en anglès perquè el nostre convidat pugui sentir les breus paraules que us donaré i com l'acte estarà gravat, doncs perquè la gent que ho pugui veure també pugui sentir les paraules. So, welcome to the Civil Engineering School. This is one of the seminars that we organize for the 50th anniversary of the Civil Engineering School. One of the former directors proposed to organize this series of seminars on the trending topics in civil engineering, and the Jesus Carrera, as former director, was one of the managing this, organizing all this series. All the series are recorded in the web, so if someone wants to listen, the other ones is welcome to connect to our web and listen all the series. I think it's a very good idea and it's very interesting. And today we have another one related to one trending topic that now we are suffering here, especially in Catalonia. So I want to thank Professor Cherry to accept the invitation. It's an honor for us having you here. And I think the room is empty, so it means that probably you good expectations, so everybody's here, and probably other people that will listen from the internet. And I don't want to say anything else. I think that Professor Fernandez is going to talk a little bit about the history of the research group on the field, and I think it's your time, Danny.
Well, thank you very much. I have a small presentation. Well, thank you very much for being here. And so my name is Daniel Fernandez, and I will try to briefly explain what is the hydrogeology group of the UPC, of the School of Civil Engineering. It's a difficult task because the group has been going on for more than 30 years, and I've been here just for 20, so that I will try to summarize some of it. Just a little of history for those of you who don't know. In the 1960s, groundwater was essentially non-existing in Barcelona, and so that the pioneering works of hydrogeology were started in 1966 and 1969 in the first serious hydrogeology study of the river basin of the Besòs and the Llobregat by Emilio Custodio, who has passed away. He just few months ago. He was an excellent professor from this school, well known by everyone. And so that in the 1967, since there was nothing and people would, there was no way of learning about groundwater. So Professor Emilio Custodio and Ramon Llaves started what is known the International Groundwater Hydrology course. So this is a well-known course, so that over more than 50 years already. And later on, and so you can see that later on the School of Civil Engineering was created in 1974, if I'm not mistaken. So that the International Groundwater Hydrology course was 7 years before the civil engineering. And then in 1984, Jesus Carrera came from Arizona, and with Emilio Custodio, they started, let's say, the hydrogeology research group of Barcelona. So nowadays, we are more than 7 expert professionals, professors of the school, and it's a combination of people from the CSIC, so that if you don't know, it's the research center of Spain, and professors from the School of Civil Engineering, and we typically have more than 15 PhDs and 4 postdocs working together. And we have published more than 1,000 publications over the years, and we work in probably all the different areas of hydrogeology, which are not just a few. And I just put here a few of them so that you can know, but there's also the web page that you can check. But we work from artificial recharge on water resources to CO2 sequestration, multi-phase flow, modeling, stochastic hydrogeology, and so on. So what if I have to characterize, and I try to be short, if I have to characterize the group by something, the highlight would be that I consider the group, it's probably one of the largest in the world about hydrogeology, and it's multidisciplinary, so that we have experts that go from basic hydrogeology to civil engineering applied to hydrogeology, geochemistry, geology, microbiology, geophysicists, geostatisticians, and environmental engineering, all working all together, which is not, this is not just easy to have, at least in Europe, and I think maybe John can say otherwise, but this is something I think it's important for us. And also there is, I don't think that there is another research group that has 2 Darcy medals. We have 2 Darcy medals, Xavi and Jesus, they have a Darcy medal, and we have many other recognitions that you can check. So highlights about the research we are doing, of course, Barcelona is suffering one of the largest droughts in nowadays. No, we all know. So that one of the solutions to overcome these droughts is artificial recharge and reclaim water. So that we work on these topics by many, you know, Paula Rodriguez Escalas, Jesus, Lourdes, Cristina, Xavi, and many, Karma, and myself. And this is not new. Artificial recharge has been in Barcelona for over 50 years. And you should know that there is a hydraulic barrier that we have to prevent saltwater intrusion with all these wells that you can see. You can see here, there is a hydraulic barrier. There is recharging wells from APAR in this area. And there are different infiltration ponds in this area. There is also, in the old days, there was also another recharging well in the Besós area. So that, well, artificial recharge is one of the biggest topics that we work on. Then, so we, starting from the initial works of Custodio, who taught us how the saltwater intrusion in Barcelona was working. So that we have also an interesting research activity that tries to understand the interaction between ocean and coastal aquifers and the aquifer. And this is mostly done by Albert Folk, Jesus Carrera, Marc Diego, and others, with many different techniques that you can check on the web. And also the other thing is that we not only try to understand processes, but we also try to develop codes and develop new numerical methods. I think that in hydrogeology, everybody knows that chemical reactions are mixing limited in porous media. This means that for a chemical reaction to occur, these two chemical compounds, they need to get together, and in porous media, this is hard to do, and so that this means that it's difficult for us to represent these reactive transport schemes in porous media. And everybody knows that the Eulerian approaches over-predict mixing. They have a lot of numerical dispersion. So that we have recently developed Lagrangian approaches to solve this. And here I put the new release that we have about the numerical model coupled to Modflow that can simulate these things, and they are ready to use in GitHub. And but this is good, but I think that the most important thing of the research group is because in the School of Civil Engineering, maybe John doesn't know, but the School of Civil Engineering, most of the research groups are excellent. There is no research group that is not excellent. And so that, but here there's something that I consider a little different, is the commitment with society, that sometimes a research group is more than publishing papers. And here I highlight several things. The first thing is that the modeling tools that we develop and we apply, and we have done this in the Besós and the Llobregat, they are typically used for in society to solve problems, engineering problems. And the other thing that I wanted to say about the commitment of the research group with society is the international groundwater course, that started in 1967. Which was the perfect match between administration, water companies, and academics. And this is not often easy to have, to see the different aspects of groundwater. And I think that for a hydrogeologist in Spain and most South America, everybody knows that if you want to be a hydrogeologist, you better take this course, no? And over the years, we have taught more than 1,500 hydrogeologists that are spread all over the world, with more than 30 students each year. And Emilio Custodio published this famous book in the 80s. So that, and with this, I like to finish and introduce John Cherry. So John Cherry is an emeritus professor of Waterloo. He's a very well-known professor. Those of you who have taken courses from Xavi or myself, probably you have been forced somehow to read his book, the Fries and Cherry book. It's a very, very well-written book. And also, so he has recently won the Stockholm Prize, which for those of you who don't know, is like the Nobel Prize of Water. And he's now in charge of a beautiful project which is known as a Groundwater project that tries that groundwater does not vanishes, and it's and tries to create sort of the knowledge in, I would say it's a hub of knowledge, right, of groundwater. And with this, I'll give you the floor to John Cherry.
Am I on? Can you hear me? Thank you for that nice introduction, Daniel. I'm really pleased to be here. When COVID was on and I was giving lectures around the world virtually, I figured this is great. I don't have to go to an airport and get on an airplane and arrive. And after a couple of years of that kind of got boring. And then I realized that getting on an airplane and arriving to give a talk and meeting people at the right place is a really nice thing. And I'm really pleased to be here. Jesus gave me a tour of the city yesterday, and I'm thinking, wow, what a nice place. This would be a great place to live. The people who live here should be happy. And I see a lot of smiles. So this is a great honor to be here. And Daniel mentioned that the research group here, in terms of groundwater professors, is large. And it's the third largest in the world, and the other two larger ones are in China. So you're the largest in the Western world. And now, by far, I would say, the University of Waterloo, where I was at, was large, and we had a wonderful group, but that was decades ago. So in fact, you're doing groundwater research and education here kind of the way it should be done. When I received, before the Stockholm Water Prize, I received the Singapore Water Prize, and it's sort of the equivalent, but it's in Asia. And when these organizations decide that they'll give a prize to a groundwater person, which is very rare, because most of these organizations don't even recognize groundwater, but after a while it becomes embarrassing, so they figure, well, we'll give a hydrogeologist a water prize. And I get these prizes because I'm the oldest, and so they don't have to think very much. We'll just give it to an old hydrogeologist. So when I arrived in Singapore, there were a lot of media interviews, which I wasn't used to. Nobody cares about groundwater, and the press doesn't interview us. But they had to, and so I was asked by a young reporter, well, Dr. Cherry, we know that you find groundwater interesting, but is it important? Is it important to humanity? Is it important to the planet? Well, I'd really never been asked that question because I travel in the world of hydrogeologists, and we know it's important, but we just don't quite know why when we're asked. So I didn't answer those very well at all, and I felt badly because my job is, to represent the groundwater community in these events. And then when I received the Stockholm Water Prize a few years ago, and I figured, oh boy, now I'm going to be asked that question again. I better get serious and see if I can answer the question, is groundwater important? And out of that came this lecture. Usually I lecture on groundwater contamination, so I'm broadening out. So there are many books written as to what's important in the world, to what's important in the future of humanity. And all of them, I think this is the most important that I've read lately. I found it by accident in a bookstore at the University of Hong Kong. And Joel Byrne Jr. is an award-winning producer of documentary films and other things, and he wrote this book, and it's a wonderful read. And so if you're going to look at something in the big picture, this is a good one. But there's an alternative view that's dominant, and this is a narrative repeated daily by the media and the politicians, that climate change caused specifically by human-produced CO2 emissions is the most urgent threat to our civilization, and all efforts must be directed at reducing human emissions. And in terms of the human suffering, which is certainly going to increase, this is an unfortunate and harmful view. So my view, the climate's always been changing, and that is a problem, but the most urgent challenge for humanity is water and food. Water is necessary for food. So if we don't solve the water and food problem, civilization as we know it will not continue to function. These are two very important graphs. The yellow graph is the population increase graph, and it's not exponential as we feared back in the 60s when I was a student. It's kind of been steady. And then we have growth rate, and so the growth rate steadily going down. This is the number of children produced. But this graph then is kind of better to talk about. So back in the 60s, when I was in my formative period, we feared exponential population growth, but it didn't become exponential. It was steady. We're now at 8 billion, and the peak is predicted to be about 2050 at about 9 billion. Okay, some projections are 10 billion, but the more recent ones are close to 9. So this is good news, because the peak is less than 3 decades away, but we're going to add 1 billion people, mostly in Africa. China peaks in 2022. So the most urgent question is, how are we going to get to the population peak without collapse of our civilization? Now, there are dozens of books like this, and this is the most famous now American, quote, environmentalist, Bill McGibbon. He has YouTube lectures and interviews and all of that, and he's got a big NGO, and he's got a lot of money that flows through his operations. Climate change is the greatest challenge that humans have ever faced. Renewable energy offers a solution. Solar, wind, electric vehicles. And now the solar, wind, and electrical vehicles, and this statement actually I think is nonsense. Now there are dozens of books by journalists repeating this narrative. And journalists and politicians who love the narrative are not scientists. They're literate, but rarely are they numerate. And because they're not numerate in general, they're very disadvantaged in drawing any conclusions on anything that has to do with science and the future of humanity. Journalists are doing a lot of harm. There's no Canadian newspaper now that has a science reporter. Such is the disrespect for science. But now, fortunately, in the last 2 or 3 years, there are very powerful books written by people, scientists with excellent credentials, that take an alternative view. Their view is like my view. Climate's important, but for the future of humanity, we've got to focus on other things. And my view then is the other things need to include water and food. Now, there's an organization that holds a meeting every year in Ricci, Italy, that I went to last year. And the title of this organization, their annual seminar, is International Seminar on Planetary Emergencies. So I went to the 55th one, attended by 90 experts from all over the world in all sorts of disciplines. And they consider petroleum, nuclear, economics, medicine, water pollution, and everything. And they agreed, which now is quite evident, that the most urgent emergency is the potential for nuclear war, which is now urgent. It was the emergency back in the 60s and 70s when I was in my formative period. But beyond war, what is the next most urgent emergency? And at this conference, there was no consensus. Everybody thought their own particular area of expertise was the emergency. Now, I represent the hydrogeology tribe, and I'm referring to journalists and hydrogeologists as tribes because we have our view, we have our biases, we have our education, etc. And in Canada and the US in the 1930s, it was a terrible period. There was a drought for 10 years. The land blew away. The crops didn't get produced. In fact, there was immense human suffering. And my parents were living in the Canadian prairies, so they lived through that, and they would kind of tell me about it. Crop failures and the rural economy collapse, much human suffering. So that's part of my family history, and that's probably how I ended up in groundwater. And that was basically a decade of climate change for which people were totally unprepared. Now, this book I just found recently, Peak Water, and peak water is an important term that you almost never see in the context of groundwater. And this book is written by a historian journalist, but very, very thoughtful. Water is a renewable resource, yet it's running out. How do we explain that puzzle? The answer lies in how mankind has developed over the last 6,000 years. So prior to the last decade or so, if you wanted to read something about the state of the environment globally, written by somebody who had good credentials and should be paid attention to, you would look at the reports and books by Lester R. Brown. And he was the founder of the World Watch Institute and then the Earth Policy Institute in Washington. Full Planet, Empty Plates, the New Geopolitics of Food Security. The real threat to our future is peak water. And he was educated in agricultural economics. He traveled widely, he had a staff, and they really looked into the state of the planet. The world has quietly transitioned into a situation where water, not land, has emerged as the principal constraint on expanding food supplies. As population rises, overpumping means some nations have reached peak water, which threatens food supply. So what do the global bureaucracies think? The World Bank, 2015. Water is reaching a tipping point. The U.S. National Intelligence Council, water insecurity is threatening world economic growth, political stability. The World Economic Forum, water insecurity risks triggering a global food crisis. So these are the pronouncements of these global bureaucracies that don't have anything to do with groundwater or anything, but even they think that water is important. And you've all heard of the 17 UN sustainability goals, but what isn't realized is 8 of the 17 sustainability goals are groundwater dependent. Okay, and that's according to UNESCO. And so that's been figured out, but you almost never hear this. Now, there's a big United Nations Global Water Conference in New York in March that I went to with 10,000 people, the first big global water conference in 50 years. And in the opening speech by the King of the Netherlands, by 2030, 1/2 of the global population will be living in severe water stress. And then he went on to say, and I mean severe water stress. That was in the opening address. So these global bureaucracies are correct that there is an immense global water problem, but broad understanding of the magnitude and urgency of the problem is lacking. We are not on a track to solve any parts of the problem, and the role of groundwater is not understood by the responsible bureaucracies. So there's no discussion at that big meeting of basically water within those sustainability goals and on whether we're tracking to make any progress. Like, quite astounding. 2022 was the United Nations Year of Groundwater. So all we groundwater people breathed a sigh of relief, saying, finally people recognize groundwater. And they produced a big book. But there was no reason to take any pleasure from this because there's no plan for real action. So it's all kind of words, and people feel good. They arrive in their limousines at these conferences, and then they go home. And their big announcement will be the next conference. So governments in our advanced technology-based society is proving to be incapable of solving this problem that our eyes cannot see. Groundwater is out of sight and out of mind, and that basically is the root of the problem. Okay, here's an important slide. Groundwater is at the heart of the global water crisis. Groundwater is 99% of all liquid fresh water. Okay, and you almost never see this 99% water because people include glaciers and whatnot, so the number goes down below 50. And I didn't even know this number until I got on this path of trying to explain why groundwater is important. But half of humanity drinks groundwater. But furthermore, 70% of global food from irrigation has groundwater origins. And much of this water is from reversible depletion, which is overdraft. Okay, the number you see published is 40%. And that's because they don't include base flow in rivers. And base flow in rivers is groundwater. So the correct number is 70%. A colleague and I published this number in an editorial, and we never see it referred to. The number we always see is 40%, even at these big conferences. And nearly all aquifers in use are contaminated to some degree, but the health impacts are minimally quantified. And usually when I give a talk, it's on groundwater pollution. Okay, there's no groundwater pollution in this talk, but if we could have another talk on pollution, which in the long haul is going to be very, very important to humanity. So what is groundwater? Groundwater is everywhere beneath us. So you can just imagine the landscape, and you drill a hole, and somewhere down there you'll find a water table, and below that you'll find fresh water. And many years ago, I was on a trip in China out into the Gobi Desert to look at the site that the Chinese have chosen for their deep geological repository for nuclear waste. And there's an area of granite way out down this road, and we're driving along, and I saw something, and we stopped the vehicle and got out, and wow, like it's a hand-dug well, like out in the middle of nowhere. You got to drive for a whole day to get there. And you look down, and there's the water table at 2 meters. What's the water like? It's perfectly fresh. Why is the well there? Because there are nomads on the desert. They used to wander around on camels with their few animals, because when it rains, there's enough green stuff for animals to actually eat. Astounding. And then you see, on the right, you see a little yurt. Okay, so there's still nomads who go out there with their animals and whatnot, and they drive little tractors, and they have their yurts. So this is where the nomads out in the Gobi Desert got their water supply. And I'm just illustrating this here because we should understand that like fresh groundwater is everywhere. Everywhere beneath us. Now, this wasn't good news to the nuclear agency because they weren't expecting the water table at that depth. They weren't expecting fresh water. They were expecting salty water, and everything they expected was in fact wrong. And that illustrates the point that there's so much about groundwater, in fact, in many parts of the globe that we don't yet still understand, and it's still a very young science. It's a good science to be studying still. Now, you see all sorts of slides like this in the media, and there's all sorts of people that are thinking about animals and whatnot. And this water you see here, well, that's groundwater. Okay, that's the water table. So if the water table drops, these little water holes dry up. And so whenever you see surface water, when it's not raining, you should realize that that surface water is basically groundwater. It gets there because it's seeping in. So groundwater is 99% of all liquid fresh water, and most of the time, most surface water is groundwater. So here's a simple little diagram, but we have a landscape, and we have a water table, and we have a well, and we're going to pump the well. And when we pump a well, the water table declines. Okay, so we're taking out water, and we're partly dewatering the system. And we're pumping the well because we want to use the water. And if we don't pump too much, the groundwater feeds the stream. Okay, those flow arrows are going into the river or stream. And streams in many places have fish, and many fish then can't live in a stream unless it's groundwater fed. So almost all the fish of any significance in Canada can only live in groundwater fed streams. And as soon as you stop feeding the stream with groundwater that provides the right temperature of water and the right chemistry of water, then you can have no fish. So pumping the well can be sustainable, but not if you pump too much. And if you pump too much, then you disrupt the river ecology. So globally, apparently, we've passed peak ecological water long ago. And as we continue to overdraft water in the global system, then we're basically drying out the continents. And on this diagram, you can see that the arrows from the stream are now going to the well. So there's no free lunch. When we pump groundwater, then we're taking water from some other part of the hydrologic cycle, and we just have to manage the hydrologic cycle. And as we see photographs like this, many of the major rivers of the world don't provide water to the oceans, like the Colorado River doesn't give Mexico any water, et cetera, et cetera. So major rivers are drying up, partly by too much water use, and then partly because glaciers are melting. So excessive aquifer depletion, we'll refer to as overdraft, and more water is pumped than recharges the aquifer from rainfall. So at some point, we're going to reach peak groundwater. And eventually, if depletion continues, the aquifer yield must decline. Now, peak groundwater is an important concept, but needs quantitation. There is no paper published in the literature on peak groundwater. And there's only one major paper published on peak water in a referee journal. That's how pathetic the whole groundwater picture is, the whole water picture is in terms of a societal perspective. I have a postdoc working on the concept of peak groundwater, and the more we get into it, the more difficult it becomes to express. So here's a very disturbing slide. Here are the largest aquifers of the world, and 1/3 are depleted beyond recovery in human time. And I don't know if this statement is right or wrong, but the people who publish it are very knowledgeable, and they've done their best to look at the information available. It might be half, it might be less, because the data are so bad. Science magazine, massive losses of groundwater from aquifer underlying California's agriculturally important Central Valley have occurred since the 1980s. Okay, so in California, which provides most Canadians with most of the fruit and vegetables we eat most of the year, okay, that's going to come to an end. And then we have this large aquifer, one of the largest productive aquifers in the world, in the American High Plains. It's called the Ogallala Aquifer. It provides 1/6 of global grain. And those green circles, that's irrigation, okay? And before all those irrigation pivots got there in the 1950s, this was basically a desert. Not known to be a desert, but the land was basically useless and hardly any people could live there. Okay, they discovered groundwater. Why in the 1950s? Because the drilling machines got better and the pumps got better. They found this amazing resource that turned lousy agricultural land into gold and just started to pump the hell out of it. That's what they do. And that's what will be done until it's dry. And here's a book by an anthropology professor at the University of Oklahoma who grew up in that area and wrote a book on it. He became interested. The imminent depletion of the Ogallala and other aquifers around the world is a defining planetary crisis of our time. He's not even a hydrogeologist. He just wandered into the field because he kind of thought he should write a book on the area that he grew up in. Now, there is a little bit of scientific literature that's saying these things. Okay, this is in a journal, Transitions from Irrigated to Dryland Agriculture in the Ogallala Aquifer. The equivalent of 40% of the currently irrigated areas and 50% of the southern high plains are basically headed, they're transitioning back to dryland agriculture. Well, what does dryland agriculture mean in this area? It means no agriculture, in essence. And the farmers are basically just pumping as hard, as fast as they can to make as much money as they can before it dries up. That's the policy. Now, India gets much worse. India has 1.4 billion people. They now passed China. 300 more million are coming. India has 1/5 of the global people, but only 4% of global water. They're the world's largest groundwater extractor, 92% for agriculture. 2/3 of the population depends on agriculture for their living. Tens of millions of farmers have water insecurity, and 400,000 farmers have committed suicide in the last few decades. Not astounding? All right, population increasing but irrigated land shrinking. So here's a paper about India from the peer-reviewed literature. Groundwater depletion is becoming a global threat to food security. Yet the ultimate impacts of depletion on agriculture and the efficacy of available adaptation strategies remain poorly quantified. In the scientific literature, you have to speak politely, and what they should say is that there's inadequate monitoring, there's inadequate knowledge, there's inadequate monitoring, and we're on a trajectory to disaster, and we don't know the speed of the disaster or the way it'll unfold. That's what these papers should say. But they don't, because that's what you can't say those things in the scientific literature. Okay, so we've got highly publicized recent droughts. And I just happened to be at Cape Town at a hydrogeology conference in 2017, right in the middle of the crisis, when the newspapers were announcing that Cape Town will actually shut off the taps. Remember that in the media? And so, like, what was that crisis about? It was basically about mismanagement. So how long was the drought in Cape Town that caused this crisis? 2 years. Like, that's not even a drought. Such is the mismanagement of water and groundwater in that area. It's a political crisis. And I was there last year, and then they've done a lot of drilling and a lot of sorting things out. But in fact, they're not ready for the next drought. Because once rainfall comes, the politicians basically lose the desire to actually do what they planned to do when they were in the middle of the drought. Sao Paulo, the same thing. I happened to be there at that time. Big crisis. And then California, well, they're always having a drought, and they had a 5-year drought in 2011, 2015, and you would think it was the end of the world. But it was kind of coming the end of the world because I was really hurting their agriculture. But it didn't result in massive changes to correct things for the future. They've been in a very recent drought recently. They had, I was actually there in January, and they had lots of rain. So the problem has disappeared. The problem with rainfall, you know, as soon as the reservoirs get filled up a little bit, then your crisis is over. And then you know more about this than I do. Europe has had a variety of drought periods, and I gather you've had more rain here in Spain, that relieves the tension for a period of time. So from a geology perspective, based on ice cores, tree rings, recharge indicators, and archaeology, climate is always changing. We've always got these variabilities. So we human beings should be planning for this type of climate change. And so the Arctic had no ice 8,000 years ago. Like, we Canadians think that all the polar bears are going to die when the Arctic gets warmed and whatnot. Well, the polar bears are there and they're fine, and everything gets adapted, but there's be a lot of human suffering. And then there was a little ice age in Europe where they had 100 years or so of very cold weather, and half the population died. So you would think when you look at paleohydrology and you would look at the history of humanity, that we humans would have been preparing for climate difficulties before all the CO2 stuff. Okay, all the CO2 stuff just maybe makes it a little bit worse. So here's a very interesting book from a hydrogeologist, retired hydrogeologist, Frank Chappell. The rise and fall of civilizations. And the rise and fall of civilizations in a major way revolves around water and drought. And he says, looking at history in light of climate change is a great way to tell the story of humanity's past. And this is the only scientific slide, I guess, in this talk, and it's from a paper that I co-authored a few years ago based on a study in Southern California near Los Angeles. And we studied an area up in the mountains in sandstone near Los Angeles, and we used rock core and chloride as our indicator, and then we compared it to tree wings, etc. And the only point of this graph is to say that the blue is when it's wet, and the yellow is when it's drought. And if we look back in the last 500 in California, we see some very long droughts that are 10 to 15 years long. Okay, a drought of 10 to 15 years is total disaster. And so are we going to have droughts in that part of the world? Well, for sure. Does it matter about CO2? Well, maybe, but we should expect them anyway. But the point being that if we remove CO2, we still should be expecting these climatic events coming at us. Disaster in Iran. Groundwater decline due to extensive overexploitation of groundwater and rising salinity levels points to dire worsening water security risks across the country. Iran is facing a state of water bankruptcy, and that's a peer-reviewed journal by a group of very respected Iranian hydrogeologists. And this is from the New York Times. In less than 25 years, Iran's eastern and southern areas will be completely deserted, and 50 million people will have to emigrate. You never see that in the news. Oh, groundwater scarcity and conflict, managing the hotspots. Water-driven refugees are now common. Drought helped cause Syria's war. Will climate change bring more like it? So two things happened in Syria. One was a population explosion from 2 million in 1950 to 22 million in 2010. Okay, then you bring drought, and the drought was 6 or 7 years long, and that gives you disaster. The Syrian war, lack of water was a trigger. A devastating drought, longest in nearly a century, massive uprising, 75% of Syria's farms failed, 86% of the livestock died between 2006 and 2011. Water and food, almost non-existent, fueled civil war. 80,000 people died. Okay, now, there are lots of things that contribute to the Syrian war and whatnot, but the argument here is that basically water and food was a major trigger. A fundamental factor. Saudi Arabia. So in Saudi Arabia, they're pumping fossil water that's 30,000 years old. So where did that water come from? It came from a wet climate, when there was a wet climate in that part of the world. So fossil water originated as rainfall when there was much rainfall and the desert bloomed. So Saudi Arabia has passed peak water long ago. But their population went from 4 million to 37 million. Okay, they just pumped their aquifers and it's fossil water, and then they got beyond peak water, so they shut down most of their agriculture. That's not a problem for Saudi Arabia because they can buy food. They've got lots of money. If they didn't have lots of money to buy food, they'd be starving. They passed peak groundwater. And this is another fossil water area that underlies Libya and Egypt and I think Tunisia, etc. The Nubian sandstone that they're dependent on. Then we've got virtual water. So food has water invested in it per kilo of water consumption in California. So hundreds of thousands of liters of water for a kilo of beef, 50,000 liters for a kilo of pork, 45 for poultry, 1,300 for rice and 1,000 for wheat and 500 for bananas. So meat is exceptionally water consumptive. So in California, much of the groundwater pumped is to grow soy and whatnot to feed cows so we can eat them. And then the person who won the Stockholm Water Prize, Tony Allen, back 15 or so years ago, developed the idea of virtual water. A very clever, obvious concept, but he developed it. Okay, and then a bunch of Dutch engineers quantified it. Virtual water enables people to live where enough food cannot be grown. So virtual water allows people to live with all the food and whatnot, but it adds to food insecurity. Now, economists will tell you that all this global trade and all that stuff adds security, but the way we're doing it, it provides immense insecurity. And here we have arrows. Okay, these arrows are food exports, etc. And the US and Canada export, and Japan imports, and China imports and exports. And the world is a very complicated system of importing and exporting food, much of which is critically dependent on irrigation. And I was in Nova Scotia during COVID, a little town in Nova Scotia, which is kind of at the end of the earth, and I looked at some asparagus in a grocery store. Wow, it's from Peru. Like asparagus in Peru in the wintertime in Canada at the end of the earth, like how the hell did it get there? Well, it got there on an airplane. Like an airplane, consuming CO2. But not only that, I found a paper basically saying that the production of this asparagus and a bunch of other things coming from Peru is based on unsustainable irrigation. So there's going to be immense human hardship because of this. Okay, food shipped out so we can buy it in Canada. The aquifers are being dried up, and the local people are going to pay the price. So it's basically unregulated, untracked globalization. And in Hong Kong, a couple of months ago, I was particularly interested in blueberries. And in this one store, there are blueberries from like 4 different countries, all flowing in. Oh. And what you don't see on the label, of course, is the CO2 use. You don't see the water use. You don't see the land degradation use. So those of us that have to have our blueberries in the wintertime, like me, we're just basically participating in global destruction. Now, famines commonly used to cause millions of people to die before the 1940s. So in 1945, the United Nations recently set up, declared that the entire world could collectively suffer a food crisis. Okay, so the Green Revolution was initiated. The Green Revolution, what's that? Okay, so in the 1950s, basically better plant genetics was brought to the table, and high-yielding varieties of cereals, especially dwarf wheat and rice, were developed, and for that the inventor got the Nobel Prize. And this was an immensely important scientific advancement. Okay, that was the start of the Green Revolution. But the Green Revolution then got extended with large tractors, chemical fertilizers, pesticides, and monocrops. Okay, and for years you would read newspapers how the Green Revolution, with all this chemical and mechanical stuff, basically saved humanity. But in fact, much of the Green Revolution was supported by irrigation, totally unacknowledged. Isn't that amazing? Because you don't see it. The farmers basically realized that they could drill deeper wells and have better pumps. So the irrigation depletes aquifers, and it's enabled the Green Revolution to appear sustainable until the 1980s. So in the 1980s, all this unsustainable stuff became evident. So when you use modern agriculture, then you basically deplete the soil by pesticides, chemical fertilizers, and monocrops, and excessive irrigation. So your soil increasingly becomes less productive, and it produces CO2 in the atmosphere. So basically that dark brown soil, that's the soil that has the organic matter. Okay, that's the natural soil. Okay, and you got to have like 4 or 5 or 6% organic matter in the soil for it to be a healthy, productive soil. The other soil produces food that's not as nutrient rich. So where'd all the carbon from the soil go? Well, it went into the atmosphere. It's a major contributor to the CO2 load. And then we've got agriculture. We've got methane, carbon dioxide, and nitrous oxide, and they're extremely important over the next few decades. Carbon dioxide is important over the longer haul. Now, this graph you can pull off the web, and I always go looking for it to see if it's updated. And if you look at it, it kind of looks like this is peak water consumption. I don't know if the data are any good, but they're always reported. Okay, the uncertainty in the data might be huge. Who would know? Nobody talks about the uncertainty in the data. Okay, but we seem to be kind of at a peak. And I've reproduced that graph on the left here, but on the right is a very important graph. The graph on the right is cumulative depletion of groundwater storage. mostly by irrigated agriculture. Depletion volume is cubic kilometers a year. And you can see that line, it's going up and up, almost exponential. But the other thing about the line, it's got a huge uncertainty. Now, I know the hydrogeologists produced this graph, and I haven't yet talked to them about it, but at least they had the courage to put on a huge uncertainty bar. So we know that groundwater is going to cause peak water to arrive as we drain these aquifers. So peak water is nearing, or has, now this is peak total water consumption, is nearing or has been reached, but total water use must eventually decline because of groundwater overdraft. So we're on a disastrous freshwater trajectory, and these Dutch guys then crunched the numbers. 4 billion people live in areas of severe physical water scarcity. And when they published this, it was basically for 1 month a year. Okay, now we're up to 3 months a year. So this prediction that half of humanity is going to be suffering immensely when we, by 2030, is based on this type of stuff. And then organizations like UNESCO are always publishing number about projected groundwater use increases. Well, that's nonsense. Okay, there's basically not enough groundwater to meet these projections. So this is demand. And the problem is that the demand can't be supplied. That's the crisis. And now, if we look at, say, China and now India, you know, people are becoming more urban. But there are 3.2 billion rural people left. Okay, these are mostly rural, poor, subsistence farmers. And if you go to Asia and you go up in the mountains, which I've done a little bit, you see this. Of course, these aren't my slides. These are wonderful slides. My slides never look like this. But you see people living up in the mountains doing terraced agriculture. Okay, and there are hundreds of millions of those people. So how can they live in the mountains? They can only live in the mountains if they've got some water to drink. So how can you live in the mountains? You can only live in the mountains if you've got springs to take water from, because otherwise you don't have water for several months a year. So mountain-dwelling people live off of groundwater springs. That's why they can be there. So the largest and most shameful failure of our society is more than 2 billion people had no access to safe drinking water in 1975. That's when the UN announced this number, and this number has increased with population growth. So now at least a third of humanity is in water poverty. And most of the people who are in this game then think it's half of humanity lives in water poverty. Okay, this is water poverty, and it looks in various forms, but it is people walking to get their water. When they get their water, it's unsafe. So basically the death rate is way beyond what it should be. Okay, that's water poverty. And I did a trip up in the mountains in Yunnan province in China many years ago, and there are lots of people living very well up in the mountains, and the governments come in and it helps organize their springs. So they dig the springs out and they put in concrete and they put in pipes, and it all looks better. The problem is it doesn't decrease the bacterial contamination at all. So your chances of dying from bacteria or viruses don't change one bit after you improve how the springs look. The United Nations basically announced with great pride, like 7 or 8 years ago, that the number of people living in rural water poverty had gone from 1.5 million to 800,000. Okay, that number is proven to be nonsense, because when you test the waters, in fact, the improvement was improved springs that look better, not actually safety. A friend of mine gave me this slide. So where population growth is highest, the rural people are scattered across the landscape. So it's very hard to get them safe water. So tens of millions of wells are needed to be drilled in rural areas. Does it have to be wells solving the problem? It has to be wells solving the problem, because the surface water is all used, it's all contaminated, so all you can do is either move the people, let them die, or drill wells. Now, large modern drilling machines are not the solution to the poorest billion who are rural and need wells, where the large drilling machines can't go to where they live. They can't get to where they should be drilling the wells, and besides they're too expensive. And the rural people then can't start their own water well drilling industry. So we in the West have brought basically the craziest ideas for how you drill wells in the really poor countries, because we brought our mindset. Now, these wells are hand pump wells, and they solve the problem. They solve the problem of enough water to drink safely and do your cooking and all of that with very simple pumps. And these wells are drilled mainly manual drilling. Okay, that's the way we drilled wells in the US and Canada back 150 years ago so that the settlers could have safe water. They figured out how to drill wells using horses and no machines. Well, those methods exist. They've been improved. This is the Bolivian method that's been improved by a German engineer. So it's amazing what you can do with manual drilling because the cost of labor doesn't matter. And groundwater is everywhere. And a bit of fresh groundwater is nearly everywhere. And we just have to access it with a plan that allows us to do that. So for the poor people who need safe water, then they can drill small household wells. Now, manual drilling doesn't do everything, and we need to develop better machine-driven methods. Rainwater harvesting can do amazing things, just like managed aquifer recharge. And it's hardly used at all. So there are places that are in drought most of the time, that have a meter of rainfall a year, such as part of India. Like, how can you be suffering drought in areas that have a meter rainfall a year? You only suffer drought if you let the rainfall run off and escape so that it's not available to use. And water filters. Okay, water filters can do wonders, but there are many of them, and they have to be the right kind, and people have to be willing to use them. So we have the water paradox. Groundwater over-extracted in many countries, less pumping of many aquifers is needed, and we need a change in diet and agriculture to not be so water-intensive. But groundwater is under-extracted in many other countries. More wells are needed for 1 billion people, but the wells only need to be small to solve the primary problems. So we need to think big on small wells, not think small on big wells, which is what we're doing. Depletion and mismanagement. So excessive groundwater extraction is accompanied by soil salinization, mostly irrigated related, seawater intrusion, and land subsidence. So here's a global mean sea level rise, and it's 2 millimeters a year, but the numbers you see now are basically 1.5 millimeters. So how can rising sea level be a crisis at 1 to 2 millimeters a year? It's only a crisis if the news meter turns it into a crisis. And this could get worse in the future as the glaciers melt, but not in the next 30 years. So if humanity is going to survive the next 30 years, it's not going to be sea level rise. All right, so what is the problem with sea level rise? Well, it's relative sea level rise. 44 of the most populous coastal cities have areas sinking faster than sea level rising, driven by groundwater pumping. So groundwater overpumping is the primary factor in seawater encroachment, not melting glaciers. And basically, 500 million people live in cities around the world that have encroaching seawater because their land is sinking. And that can be prevented by better engineering and all the things that need to be done. Okay, so this was a famous book back many years ago that I bought and read and didn't think about it. So as a society, we're choosing civilization collapse by ignoring what science is telling us. And we have 5 pillars that determine the state of humanity and the planet, and fresh water is key, soil, oceans, forests, and climate. And 1, 2, and 3 then are basically fresh water and food. So 1, 2, and 3 are strongly dependent on groundwater. So if humanity faces the perfect storm, okay, we're at or near peak water, we're apparently past peak soil, and we're still cutting down forests to make soil that then erodes and then disappears, mostly to eat beef, and we passed peak ocean fishery. Now, after 30 years of emission reduction efforts, the rise, we're reducing our emissions, and it's leveling off, but we need to redirect efforts at these other problems to water and food. The emissions problem is kind of taking care of itself slowly, but it's not the crisis. So humans have immensely altered the Earth's surface. So if we want to believe that a bit of CO2 is going to do us in, we need to look at the fact of how immensely we've impacted and changed the Earth's surface. Much agricultural soil has become less pervious, so much more rainfall runs off, so we got much more flooding. Every time there's a flood, the media blames it on climate change. They don't blame it on the stupid way that we manage our land. And 1/3 of all land originally in forests has been converted to other cover, mostly farms, etc. So we humans have basically exceeded the carrying capacity of the Earth. Okay, that was a big deal back decades ago. My generation feared exceeding the carrying capacity. But we've exceeded it by our stupidity in the way that we're managing the environment. Oh, and we're doing it by subsidizing it. So here's a statement about the EU. Direct payments to farmers. The program is the most expensive scheme in the EU, accounting for more than 40% of the annual budget. Okay, so we're subsidizing the type of agriculture that's basically unsustainable. And it's similar or worse in the United States. So on the left, we've got our agriculture that gives us our wonderful food that's kind of laden with pollutants, but it looks good. And on the right, we've got these other types of agriculture, which those people who study the problem say that we have to go to regenerative agriculture, and there are various forms of it. Mixed crops, indoor factories, ecological agriculture, all these various different types of agriculture that you hear about. And no one single one is a solution, but we're going to have to do more and more of it. Okay, so then we have sources of energy. So you hear this nonsense about renewable energy, okay, and environmental friendly energy. There is no environmental friendly energy. How can we even think that? So a few weeks ago, I took down the solar panels on my cottage, and they're 25 years old, and they're junk. They're not producing any power. Okay, I phoned the government. What am I going to do with them? Take them to the dump. So in fact, my solar panels are only renewable if my money's renewable. So now I got to replace them. And the same with wind. And the wind blades, they even last less time. And so solar and wind are going to be amazingly positive things. Okay, they're replacing coal, and when they replace coal, that's what we need to do. But we should never think of them as renewable. And they're highly damaging to the environment. Like, look at those windmills out in the ocean. And when you look at what the ecologists say about that, like, that's environmental insanity. And we're putting it out on the ocean because people don't want to have them on land. And these solar farms that go on as far as the eye can see. So now we've got hydroelectric. And we have a lot of hydroelectric in Canada. And so I rode on a five-star floating boat on the huge reservoir behind the Three Gorges Dam in China about 10 years ago. As the reservoir was filling up, I rode the boat to Chongqing, which is at the other end of the reservoir. And you could see the worst devastation that you could imagine. Okay, the Three Gorges environment is a beautiful environment. And all the communities along it, the water was coming up, and you could kind of see the devastation and the hopelessness of it all. 3 million people had to be moved. Okay, that dam didn't need to be built. Now China could replace that energy with basically 2 years or 5 years of building nuclear reactors. And the hydraulics department at Tsinghua University basically wrote a letter to the president saying that in their opinion, building the Three Gorges Dam was a mistake. It was a political dam. The dam in Egypt was a mistake. The Aswan Dam, all the big dams are political dams, and most of them turn out to be a mistake. So let's not refer to that as clean environmental energy. At the end of the day, then, nuclear is the most responsible. Finally, then, at the last conference that the UN had, they've agreed that nuclear now is classified as green. Can you imagine nuclear not being green? It's got the least footprint of all. But it was done in by propaganda, done in purposely by propaganda generated in the 70s by the coal industry and the oil industry and the environmental industry. No deaths from nuclear, no large escape of radioactivity, not even significant deaths at the Russian nuclear reactor. So nuclear was demonized by coal, oil, and environmental industries. Arguments against nuclear are based on unsafe, fosters nuclear weapons, and safe burial of waste. The Canadian nuclear system we do not enrich our uranium. Okay, it's a can-do reactor, it's unenriched uranium, and you can't make weapons out of it. So if you're concerned about weapons coming from nuclear power, then you can build the Canadian reactors. They're safe in terms of safety, the calculations all show that. And safe burial of waste. Well, the hydrogeologic community has been telling the nuclear industry for 30 years that deep geological repositories are safe. Okay, and it's the safest place to put you. Just dig a mine down at 500 meters, and the plans for nuclear waste are the safest burial of any hazardous material. I mean, they're so safe and so expensive, it's beyond belief. In the meantime, we emit all sorts of other more dangerous chemicals to the environment, such as PFAS, the life chemicals. So it's my understanding that the only country that has a large science-based plan to reduce oil use is China. And China offers some hope by leading the way. and they're going nuclear. Now, if you're interested in the carbon cycle, you can go onto the web and you can look at papers like this one, published basically last year in a very prestigious journal. This is the carbon cycle. This is the cycle that we're all supposed to be worried about. And when you look at the numbers, the question is, well, do the numbers make any sense? Do they come from good science? And then in the paper, they admit that there's some huge uncertainties, particularly with the carbon dioxide coming across the land surface, the carbon dioxide from the soil. And that includes the carbon dioxide from groundwater. And that stuff isn't quantified in any way that you could basically refer to as being science. And this is from a diagram in a book I published long ago, but basically it shows that you have the production of CO2, okay, and a bunch of arrows going off to the atmosphere. So, but basically the CO2 forms carbonic acid in the soil, but the soil produces CO2 because the plant roots produce CO2 and the organic matter gets oxidized. So the soil zone is a huge producer of CO2, relatively unquantified, and you never hear about it. Oh, and if you want to get confused, then here's the statement. Water vapor is the Earth's most abundant greenhouse gas. It's responsible for about half of the Earth's greenhouse effect. Now, people argue about this, and I have no idea whether it's correct or not, but this is a statement from NASA. The point I'm making here is that the whole water cycle has been disrupted by humanity, and we don't understand it. All right, look at this. So here we have, this is our groundwater, this is our water use consumption graph. And at the top, we've got evaporation. So we built so many dams with so many reservoirs that evaporation is one of the main consumers of water. So, like here's all this irrigation. Look at all that vapor. What does irrigation do? It puts water vapor into the atmosphere. What does it also do? It puts CO2 into the atmosphere. How come? It's because basically the CO2 dissolved in water in shallow groundwater is 1,000 times the CO2, 100 or 1,000 times the CO2 in normal water. So as soon as you expose groundwater, it emits CO2. Now, there might be somebody in the audience that says, well, I've calculated how big this is, and I think it's trivial. And I'd be glad to hear that. The fact that no one ever tells me that is part of the problem. I have a colleague, a very elderly colleague, who's trying to do the calculation. Every time he does it and whatnot and so forth, he submits it to nature and gets turned down. So then he does it again. But anyway, the story of nature not being a scientific journal is another story. All right, the planet is extremely drought sensitive. Okay, groundwater and food facts. 40% of global agriculture is by irrigation. 70% of irrigation is groundwater. This includes 40% from wells and 30% from base flow. So during long drought, nearly all food comes from groundwater because it has to. Humanity is wrongly distributed across the planet. So we can't say the planet is overpopulated. It's just that the populations are wrongly distributed. Not that that helps. But so 30% of the population lives in deserts and drylands. See, they're depending then on irrigation or on rainfall being consistent. And 40% of all cultivated land is in drylands. All right, so engineers like to build dams. Hydrogeologists like to drill wells. But engineers run the show. Surface water engineers run the show. China has 87,000 dams. Apparently the US has 84,000 dams. And in the world, we've got 200,000 dams, okay, to basically store surface water that then when the climate changes and gets hot, evaporates. So apparently one of the problems in France now is that they're having to produce less nuclear energy because they don't have enough fresh water in places and whatnot to cool the reactors or whatever. And then I read there's so much standing water in the northern hemisphere behind dams that the weight of the water has tilted the Earth's axis, affecting the spin. And I haven't tracked this down to see where it came from, but this is the magnitude of the change that we humans have made on the water cycle. This was a very famous quote back in the 60s. I was a student in California. If you're not part of the solution, you're part of the problem. What should universities do? They're part of the problem. Universities should develop a multidisciplinary course on the state of the planet that all students must take. For this, there would have to be a rigorous dialogue and debate between the many relevant disciplines and specializations. We'd have to tear down the discipline silos, and we'd have to make sure water and food are the key elements. So in my travels, no university teaches a course anywhere near this. And when I talk to the professors, we all agree that that should be done. And all the professors agree that they could never do it at their university because the universities are incapable of enough change to do that. Isn't that amazing? You'd have to get a bunch of professors together, and they'd all have to kind of work on the problem in a systematic way, and then you'd have to put it into a course and get people to take it. And students want those things, but we professors can't do that. So is anybody doing anything useful? Well, we have this little Dutch underfunded group, the Water Footprint Network. The uses of the water footprint concept to promote and transition towards sustainable, fair, and efficient use of freshwater resources is critical. These are the people trying to calculate the water impacts then in everything we use. Okay, at the end of the day, when we buy our food and I buy my blueberries from Peru, okay, I should see in the package what the loading is, what the environmental consumption is. It should have water and CO2 and all of that. And if we don't get to that, then we consumers have no way of having an input, and then we have to depend on our innumerate and illogical politicians. So if humanity is on a trajectory towards immense human suffering as water does not get fixed, there's the wrong narrative. Okay, that's this whole reducing CO2 as the most urgent need. It's a need, but it's not the urgent one. And if you remember anything from this lecture, please remember this: 99%, half of humanity drinks groundwater, 70% of global food, and nearly all aquifers in use are contaminated to some degree, but the health impacts are minimally quantified. Some aquifers are perfectly safe to use and they can be used better. Other aquifers, parts of them shouldn't be used. And this is basically the elephant in the room. And it's my main area of expertise, and I don't even have an opportunity in this talk to expand on it because I've had to cover all these other things. The harm being done by contaminated groundwater is very subtle, and the numbers are very obscure. But there's also an energy crisis. So if this was an energy professor up here talking, that person would tell you about this crisis. Half the people in the world suffer from energy poverty. Okay, that means you're cooking from wood or dung or whatever. That's what that means. And that's the end of this lecture, and I thank you for your attention. And if you want to know more groundwater, just look up this on the web. Thanks for your attention.
Thank you very much, John. So now is the time to challenge what he said. If you don't challenge it, is that you agree? Any question?
Yeah, don't accept what I'm telling you. Okay, I'm hoping that I'm wrong on some of these points. And at every talk I give, I'm hoping that somebody can tell me something optimistic.
Okay, Jordi Bruno.
I should start first congratulating you, because I think you have come to that point of life when you can say what you think about it.
I can.
And that's a privilege.
It's a privilege. Yeah.
I'm getting there, but not yet, so I'll be a little bit more careful.
You're right, it's a privilege, and that's why I get on an airplane and do this, because in fact it's a privilege that I have to take advantage of.
Yes.
Thank you.
Thank you. The second thing is a little bit, not a challenge, but maybe a way of, normally it's not a good strategy, I'm sorry to tell you that, to confront one issue with another one, saying, you know, climate change is now definitely driving our lives, whatever that is. Yeah, I've been working on that since '86, so I know I was one of the pioneers. Water scarcity is definitely there. Probably the intensity of the problem, or for me at least, of the urgency of the problem is definitely on water scarcity, because that's really there. And you know, whatever we do with CO2 reductions, and I'm sorry to say that, but I'm getting old also, it won't improve the situation immediately. Okay? Because CO2 has a time of residence in the atmosphere, and but nobody says that, because then it's not part of the line, right? Yeah. So I really agree, and you see, you have revamped on a little bit the spirit when I started what now is AMFOR 30 years ago. in terms, I know, but it's the only thing I'm going to say, that water is the number one problem we should be
Yeah.
worrying.
Yeah.
And I think because of what we have in here, we are very privileged also to be able to do that.
Yeah.
That was just my comment.
So as I give this talk in the last 2.5 years, I have to be very careful of my strategy. And early on, my colleagues would say, John, don't say anything about CO2. Okay, don't get into that environment because you'll piss people off, you'll lose credibility. And then I found other scientists are writing books on this. So things have changed in the last 2 years. So now I'm doing it the way I'm doing it, but however I do it, the point is to do it with the most effectiveness. So that's what you're talking about. So we have to figure out how I present this. So if I disturb you, or if you think I appear biased, or if my strategy isn't the most effective strategy, then let me know. I'd be glad to hear. Now, talking positive on nuclear, I couldn't do that 2 years ago. But now, like, there's a nuclear renaissance. It was declared to be green at the last conference. Before that, I'm saying, like, nuclear isn't green? Are you crazy? So nuclear now has gone from being in a back barn where only crazy people talk about it to me being able to talk about it. Now, early in my career, then I was funded by the nuclear industry to study radioactive waste. So I got to talk to the engineers and the vice presidents, and we had great enthusiasm in Canada at that time that nuclear power would basically be the future of humanity. That dream is coming back. Once you get beyond the wind and the solar, nuclear is the hope, and China's embraced it. And the new reactors then don't have a waste problem. The new reactors, the thorium reactors, apparently don't have a heat problem. So not only did we stop building nuclear reactors, we stopped doing research. And nuclear was going to be the savior of humanity. So France is the greenest country in Europe because they got to 80% nuclear. What did the French do? They just decided to build nuclear reactors up to 80%. And they built them all in a 10 or 15-year period. We in Canada built our reactors in the province of Ontario in the same period, but we stopped. We just kept building them. And if we kept building it, we would have no issues on our emissions. And then we've got these big hydroelectric projects, and they're tragedies. Like, we built some in northern Canada that disrupted the people. They're emitting methane because of the way the system works. And so when we humans go into an environment and we do our big engineering projects, in many cases, we have no idea what the impacts are. Now there's a bigger dam being built in China. There's one free river left in China. It's the Nijiang River that I visited many years ago, and it's a beautiful river. It's got rapids and everything. If it was in North America, we'd be rafting down it. And so when I asked the Chinese engineers, are you going to dam the Nijiang? And they all say, I hope not. But damming rivers is always a political decision. But they can build nuclear reactors in 5 years cheaper than damming a river. So maybe they'll have one river left.
Audrey.
Thank you for your great talk, Professor Cherry. One question. One of the big ideas in your talk is that the problem is just that people are not distributed the same way that water is distributed, and food growing is not distributed the same way that water is distributed. Do you have any ideas about how we incentivize a solution? Because I think about this in Arizona or here in Catalonia, people want to live in these beautiful and economically productive places, but maybe the water can't support it. What data sets and systems do we need to come up with a solution and implement it?
So, I mean, I live in my groundwater tribe, and our tribe rarely is asked to think in the bigger picture. The tribes that are asked to think in the bigger picture are in the environmental schools and in some engineering departments. So if I were to, so I'm an amateur. But as an amateur in my attempt to become informed, what I'm finding is that most irrigation is so inefficient. So we in our modern industrial society are operating on old science, old technology, old monitoring. So Israel is an example of a country that uses water and exports food. So in essence, all these problems are, at the end of the day, they're political. But our politicians are poorly informed, and so how are they poorly informed? They're not being informed by the government agencies properly. So if the Canadian Prime Minister ever wanted to be informed about anything, which he doesn't, and he asked in the city of Ottawa for advice on water, he wouldn't be able to assemble a group that could carry an intelligent, holistic, organized, responsible conversation on water. And the whole business of interdisciplinary science, or we might call it multidisciplinary. And back in the 70s and 80s, that was very common in universities. Everybody said, well, we're going to do interdisciplinary work. And they tried, and they gave us professors big grants. We'd all meet, we'd get our money, we'd divvy it up, and we'd all go back to our office and do our little thing. So interdisciplinary holistic science is the first step. And it's easy to blame our politicians and water agencies, but they're basically not being provided what they needed. And for younger people, there's so much exciting work to do at the interfaces. Okay, if you're in the heart of a discipline, almost all of the good stuff has been done, so you're going to work very hard. If you go to the interfaces between disciplines, there's all sorts of exciting stuff. That's what I do if I was doing my career over. So in Spain, you're kind of a microcosm. You've got drought, you've got all sorts of different sources of water, you've got big research groups, your politicians know that water's a problem, you're an advanced country, and so you need to provide leadership.
I am not sure our politicians. Our politicians, like those everywhere else, are concerned about being elected, which is a short-term, issue.
Yeah.
Huh? Oh, yeah. But well, I am younger. I am much younger than John, but I can start still saying what I think. Is there any other question? Yes, Bella.
Thank you, Professor, for this presentation. It was really nice to share this wisdom that you share with us. I have a question like a PhD student. Something that is around and this came with the politicians and these things. If this kind of scientific improvement, how can be applied or how can be connected with the politics in the country, you know? Because we are working with some kind of idealisms that we can, you know, share this with the society in some way. But sometimes when you finish, you feel like it's another thing, you know? So I want to know what you suggest.
I mean, it's so easy to criticize things at the political level, but if the universities and the disciplines haven't collaborated so that we can actually present to the politicians and the water managers a balanced, informed, multidisciplinary view, then in fact we're the problem. So when I started to branch out and whatnot, and I found terms like peak water. Well, I haven't heard of that. And there's one paper on it by a guy in California, peak water. It has almost no citations. Like, what's more important than a peak water concept? And it fell on deaf ears, and peak groundwater then, that's in these books by journalists, then hasn't been quantified. Peak oil is well known, and in fact, calculating the production peaks for oil reservoir is standard technology. And all the oil reservoirs of the world, they've calculated that. Okay, that's critical if you're going to develop, so they produce, and they got a peak, and then it goes down. And when you take all the peaks in all the oil reservoirs, and you add them all up, then you get to peak oil globally. Okay, and that number is predicted, and maybe we're at it now or next year and whatnot and so forth. Now, there's peak conventional oil, and there's peak new oil, and all that gets in there. So in fact, we in the groundwater community, we don't even have the numbers to have an intelligent conversation. So the peak groundwater, we probably passed it. So Africa has lots of groundwater that's not developed, but they don't have to pump a whole bunch of groundwater. So the people who say, well, we got to use groundwater in Africa, everybody says, well, yeah, but they're going to have over pumping problems. No, in Africa they haven't developed the groundwater, and they need to. So I guess, you know, when you get right down to it, the problem lies with the scientific academic community. The academic community, because we have freedom. Okay, we protect our freedom. We protect the right to have tenure and all that stuff. Well, why are we so strongly protecting our freedom, we professors, when we don't do anything with it? Yeah, so universities are a problem. Oh, so this project I'm leading is basically to get experts around the world to write books about groundwater and whatnot and so forth. And we publish them on the web, and we've got lots of volunteers, and we need a bit more money and all of that. But my hope now is to start publishing books on exemplary cases. So for example, the China Geological Survey is installing 100,000 monitoring wells so that they can keep track of their groundwater. 100,000 locations. Each location, several wells. They're doing it like an army, because that's what's been ordered. And it's unbelievable. Modern technology done by the right people. So that's exemplary. So the world needs to hear about that. So I need to get them to write it up. And there's a city in Canada, Guelph, that actually monitors its groundwater. They actually know what's happening because they work with the research community. So that's exemplary. And so as I go around the world, I'm trying to find, like, what's going on that's exemplary. So we got to know here what's going on in Spain that's exemplary. You're ahead in managed aquifer MAR, managed aquifer recharge. You're ahead on that. Your scientists know more about it technically. So we have to have that written up. One of the problems is everybody who's at the leading edge or somewhere near the leading edge is too busy. So like we're all too busy just getting through the week, doing what we need to do to get through our jobs, while the really important stuff doesn't get done. So Spain has an opportunity, like all countries have an opportunity to take what they're doing that's better than other countries. So the problem with groundwater is all groundwater problems are local. Like they're all local, a city, an area, a region. So then we kind of think, well, no point in writing that up and whatnot and so forth because it's local. But the same problems are all over the world. And that's a problem we hydrogeologists have. And now hydrogeologists are basically, they're going extinct. So the number of knowledgeable hydrogeologists in the world are declining because of the educational system. Young people don't go into groundwater, they go into whatever's popular. Many of them go into environmental science, like what's that? Or they go into sustainability, like what's that? All those things have to come from grounded science. And environmental science is where the action is, but it can't just be environmental science, it's got to be really good stuff in all the little pieces. A lot of ranting, eh? Sorry.
Thank you very much, John. It's been a very nice talk, nice discussion, but I think we have to finish now.
Yes.
So thank you all for coming, and I hope you enjoyed it.